Welcome back. Did you know that when ice cream sales are at their highest, reported cases of the flu are at their lowest, and vice versa? Does this mean ice cream cures or prevents the flu? I think not. But this seasonal oddity makes for a fun beginning to this week's material on correlation and regression. Here we test the relationship between two variables to see if increasing one corresponds to an increase or a decrease in the other. We expect to see those who practice their free throws more will have a higher free throw percentage, or those who study more will get higher test scores. But does red paint make your car go faster? Well, explain why red cars are flagged for speeding more than any other car. Could it be that sports cars are mostly red? And why is it that people who spend the most money tend to save the most money? Could it be fate? Or a bailout? Or maybe just that they make more money? Why is it that babies that nap in their own beds are healthier? Could it be linked to the use of daycare maybe? And should worried moms just carry a bed to daycare to make their babies healthier? Or will this prove to be pointless? Some variables have truly predictive relationships, and knowing one value can lead to accurately predicting the other. But often any relationships between variables, even strong ones, can be explained by something else, like the time of year or some third undisclosed variable. This is truly the most used and most abused technique in all of statistics, as it is a great tool, but without an understanding of the variables, people can be so easily duped. Infomercials thrive on suspicious correlations, but the wise consumer of statistics knows better than to trust results just because there's a stack of data on the table telling them just how this product will perform a miracle for you. In this unit, we'll explore not only the strength of the relationships, but the equation that enables you to predict one variable from the other. And all you need is good data, Microsoft Excel, and your wits.
Unit 7, Correlation and Regression. In this unit, we're going to look at testing relationships between two variables in which both of them are scale, coming up with a model where we can actually forecast one variable from another, and then we're going to look at multiple regression where we will have three or more variables where we'll use many variables to predict the value of one variable and try to come up with the best model that does the job of predicting. Let's start with correlation. Correlation, you can see in the name itself the word relation. It is a measurement of the relationship between two variables. And we are looking at scale variables, again, because we don't measure relationships this way for nominal categorical type variables. Chi-square tests looked at studying relationships. It wasn't quantified, but it looked at studying the relationship between two categorical variables. In this one, we can actually measure a degree of relationship between two scale variables. And note, being correlated does not mean that one causes the other. This seems to be a common misunderstanding that people see there's a correlation and say, therefore, we can say that this causes that. That's not true. There's so many examples I can throw at you that would demonstrate this point. Like, I'll bet you'll find that a car that gets speeding tickets the most turns out to typically be painted red. Gee, does red paint make the car go faster? The truth is they are more often tagged for speeding tickets. Why? Because most sports cars are painted red. But the red paint doesn't cause it to go faster. So the paint does seem to be related, but it's not causal. It does that trick. If I were to have husbands and wives arm wrestle each other, and then we looked at the salaries of the two people, we're going to find a relationship between winning the arm wrestling match and making more money. Turns out the people who wins the arm wrestling match more often makes more money. Does that mean that you end up making more money because you've got bigger biceps? No. It really is the fact that men tend to make more money than women. Men are more likely to win an arm wrestling match, but winning the arm wrestling match does not cause you to make more money, unless, of course, you use your muscles to browbeat your boss into giving you an increase. That's not the case. If I were to ask mothers of young babies, less like 6 months of age or younger, how often do you burp your baby? And then I also checked into how often their baby gets sick. I bet you'll find a relationship in the number of times a day that a mom might burp their baby and how often that baby gets sick. Heck, if I asked them how many times a day do you change your baby's diaper and how often they get sick, I'd find a relationship. Why is it that the ones where the moms change the most diapers or burp their babies the most tend to have the babies that get sick the least, and vice versa? Is it because diaper changing and burping prevents illness? If you believe that, then you might start buying the new Baby Burp Me product or something like that and say, now I'm going to make my baby healthier. Or you're going to wake your baby up at 4 in the morning to get in a few extra burps just to make the baby healthier. Well, we know that's silly. There's a reason for it. A reason being that when the moms do it the least, it's because the babies are in daycare. If the baby's in daycare, then someone else is changing the diapers and burping the baby during the day. Parents have limited opportunities to do it, so the baby is more likely getting sick from daycare. But if we're not focusing on that and we focus only on what's being measured, you might jump to the conclusion that burping your baby makes them healthier, changing their diapers prevents illness, and whatever else. As silly as they sound, we tend to think that quite often and think that correlation means causation. And it clearly doesn't. When we do a correlation analysis, we start out with 2 variables. We'll call this a simple correlation. One of the variables we call an independent variable, designated normally as an X variable, and the dependent variable is designated as the Y variable. That goes back to the algebraic days where the X-axis is the horizontal axis and the Y-axis is the vertical axis, and the formulas were always Y equals mx plus b. You plug the number into the X, out comes the Y. So what goes in, what comes out, that's crucial. You have to ask yourself, what is being used to predict what? Okay? What's the one that you're telling me, and what's the one you're actually trying to predict? What we would first do when we have data is create what we call a scatter plot or scatter diagram, as they're called. We take each XY value in the data set and plot them. And once we plot all the data points, we look at the pattern. It could clearly show a linear pattern, which means they tend to go in one direction, upward or downward, not necessarily right on a line, but they basically are going, it may be almost like a tube going in one direction. So the data might be spread out somewhat, but it's going in one general direction, trending upward or trending downward. That's what I mean by linear. Maybe the data has all kinds of weird patterns. It's curved. Kind of goes up and down and up again, or it makes some U-shaped curve. I mean, who knows? It could be anything, in which case we clearly do not have linearity. Or maybe it looks like just one big circle, and it's evenly sprayed, and we definitely have no linearity there. Now, clearly, in the first case, we have linearity. It seems to be going in the right direction, upward or downward. We have something worth continuing on with. The other two, I would say, I don't see any reason to even bother doing any analysis here. It doesn't look the least bit linear. If it doesn't look like a duck or quack like a duck, why on earth would you even consider it being a duck? So now we look at this and say, okay, this one appears linear. Let's continue. We load the data into our Excel file, and we have to make sure we're distinguishing which one is X and which one is Y. In a file I've got here, I've got 2 different variables, one for ads and one for sales. We would expect that the more money we spend, or the more advertisements we run, the greater amount of money we would make in sales. So in that particular case, the ads are our independent variable, and the sales are our dependent. Ads go in, sales come out. How good is that relationship between those 2 variables? Well, when we measure correlation, the correlation has a range of anywhere from -1 to +1. +1 is an absolute perfect correlation on a straight line. All the dots are on that straight line and it's going upward. While -1 is a perfect inverse correlation. All the dots are on a straight line going downward. Can they both exist? Is it possible to have a perfect correlation or a perfect negative or positive? Absolutely. We don't mess with them very often because it's kind of boring. There's not much to do. If I were to do a correlation on the temperature in the rooms in the building in degrees Fahrenheit and in degrees Celsius, and I plotted those points, you would find that they would line up in a perfect line. The higher the degrees Fahrenheit, the higher the degrees Celsius, and it's perfectly predictable. It's because there's a formulaic approach to it. We can convert Celsius into Fahrenheit by multiplying by 1.8 and adding 32 to it, and there's no margin of error. It is exactly that. So that would be a case of an R equals +1. It's right on the line. A case of R equals -1, well, if I were to look at every team in Major League Baseball, they play 162 games in the season. I said, tell me how many games they won, and I can tell you how many games they lost with absolute perfect predictability. They won 90, they must have lost 72. They won 80, they must have lost 82. Why? Because we know exactly how many they play, and the more you win, the less you lose, and vice versa. It can be computed perfectly. That would be a case of R equals -1. Once again, boring. We don't need to work with those. R's in the range of 0.7 to 0.999, whatever, they are called strong. They are very predictable. The higher one is, the higher the other is, and you pretty much know when you have those. The scatter plots look like they're just huddled around the line. It's not right on the line, but they're really close. You could definitely see no outliers there, and they're all going in that one direction with some degree of spreading, but not much. An excellent example would be if I were to plot the miles that each person went in their cab from the airport to their home and what the cab fare was for each of them. You wouldn't be surprised to find out that the people who actually went the furthest paid the most. The ones who were the closest paid the least. Well, the cabs run on a meter. The meter is based on mileage. So it should be almost perfect, but it's not quite perfect. The meters may not be calibrated. A person might have gotten stuck at a railroad crossing, in which case the meter will go up just because you're sitting still. So there's a couple of oddball things that can happen. But the correlation will be strong. I can pretty much assure you it's going to be at least 0.95. It's on the strong side because it's very predictable from one to the other. You can have a moderate correlation, which is in the 0.3 to 0.699 range. That's where it still has some degree of predictability, just not quite as strong as like the taxi cab example. You're going to see the data spread out some more. So yeah, you still see that the trend is going up or the trend is going down, but you're not going to see the points all huddled around the line. You are going to see some spread out a lot more. You might see an occasional outlier or two, but that's still a good correlation. And once again, we call it moderate. It's 0.3, but less than 0.7 in that range. If I were to try and run a correlation for a person's SAT score versus the GPA they got in college, SATs trying to predict your GPA, you would find that kind of relationship. They're not perfect predictors. They're not even great predictors, but they're good predictors. Those who do better on the exam tend to do better in school and vice versa. So they're good predictors. Less than 0.30, we call them weak. I don't even like to waste my time with them. Basically, you'll see the data all over the place, and the only thing that makes it not zero is if the data is not perfectly symmetrical. If I drew the data in one circle and made it a perfect circle, that would be a case of R equals 0. If I've got one stray dot anywhere, it's going to change it. So you're not likely to ever see R equal to exactly 0. It's going to be slightly off. So you can have some really pathetic correlations in there. I wouldn't get excited about, hey, I've got a correlation of 0.02. Doesn't really do much good for you. There's another statistic that we calculate called the coefficient of determination, which is the R squared. That tells us the percent of the variability in the Y variable that you can explain basically from the X variable. Well, how come your cab fare was not as high as my cab fare? Mine was twice as high as yours, but I went twice as far. Well, that explains it. We can use that one variable to explain it. There's some margin of error because, like I said, railroad crossings and the meter might not be calibrated, but I might be able to explain away almost all of it. So if the R was 0.95, that means when you square 0.95, you get 0.9025. You've explained away about 90% of why one fare is higher than another and one is lower than another. And there's still something out there that isn't explained yet, some error in the machinery or whatever. But you explained away over 90%. When the R is exactly 1, well, R squared is 100%. You're saying, well, I can explain 100% of why this room has a higher degrees Fahrenheit than this room because it's higher in degrees Celsius. Okay, with perfect precision. So an R of 0.7, which I consider to be strong, R squared is 49%. A strong correlation is one that basically at least half of the variability is explained away by that relationship. The other half, well, there might be more variables that you need to look at, but one variable single-handedly can explain away at least half. That's what makes it strong. A moderate correlation can go down as low as 0.3. Well, 0.3 squared is 0.09, which is 9%. That means I consider a relationship to be moderate if it can at least capture 9, 10% of why this is higher than this, why is this lower than this. You can get 1/10 of the explanation captured. I still consider it valuable. That variable is adding something valuable to our understanding just by having a correlation of 0.3 and contributing essentially at least 9%. Anything less than that, think of what little contribution you're making. When someone gets excited about, I had an R of 0.01, well, 0.01 squared is 0.0001, which is 0.01%. That means they explained away 1/10,000th of why something is the way it is. I remembered going to a conference one time where someone was presenting his future dissertation, and he was bragging about how he has proven what causes turnover. Well, that's a big mistake right there, saying you've proven what causes why people leave their jobs or get fired. And then I said, I asked him about his output, and he told me that he had a correlation of 0.01. And I said, but that means that you only explained away 1/10,000th. And he said, yes, but it was statistically significant. And he was excited about that. Unfortunately, that happens. With tests for correlation, you might get statistical significance even if it's a pathetically weak relationship, because the test for correlation is merely testing whether or not the correlation is 0. And so it could be 0.01. As long as there's enough data there, you might reject the null and say, yep, I found correlation. My personal feelings, even though you ran the test properly and you found that you do have correlation, if that correlation is on the weak side, I really wouldn't be bragging about it. I would say, well, okay, we found a correlation, but it is weak. Would you want to buy a drug just because the FDA says, well, we have proven that using this drug will likely have an effect on reducing your blood pressure, cholesterol level, whatever? If it turned out that the R was 0.02, that meant we've explained away 0.04% of what causes cholesterol to go up or down. And you're going to trust this drug just because they said they got statistically significant results. You really need to have more than that to go on. But nonetheless, the test does allow this. If we take a look at the output here, you see there's many different parts to it. We had 10 observations in the data set. Correlation coefficient for the ads versus sales of 0.978. Very strong. More you spend on ads, the better your sales will be, and it's pretty predictable. The coefficient of determination, 0.957. That means 95.7% of the sales going up and down can be explained away by our ads being higher and lower. Wow. If that isn't a push for advertising in that company, I don't know what would be. The equation itself, you could see, we take the actual variable names that you enter, which in this case are sales and ads, and we come up with sales equals 5.134 plus 2.017 times ads. That's your y equals mx plus b formula. We've got the y-intercept, and we've got the slope. We've got the x variable, we've got the y variable. You plug in ads, you multiply it by the slope of 2.017, you add 5.134, and you get sales. So we can predict what the sales would be based on whatever amount of ads you're running. And you can see right below it, we do just that. You plug a 20 in for the x value using 95% confidence, and it says we predict the sales for ads equal to 20, we predict sales of 45.477. And this is in thousands of dollars. So we would predict $45,477 in sales if we had spent $20,000 on ads. Below it, it's got a confidence interval and a prediction interval. That's just the margin of error. We're saying that for a prediction interval is based on a single value. for a single instance where I spend $20,000, I would expect to make $45,477, give or take $8,535. So it could be $8,500 higher, $8,500 lower, but it's somewhere in that range, and I'm 95% sure. The confidence interval said, on average, if I spent $20,000 every single week, on average, I could expect to make $45,477, give or take $2,978. So the confidence interval is looking at the average results. Some weeks it'll be a little higher, some a little lower, but on average you should expect to be in that range. For an individual value, you have to give yourself more room for error. Now, I plugged in a 20. I could have plugged in more, could have plugged in less, but I'm limited. If you take a look in the data set, the most spent on ads out of that data set was $32,000. The least was $5,000. Don't plug in any number that's lower than 5 or higher than 32 because it's outside the range of the data. This regression model was created based on this data set. So if you don't have data outside that range, making a prediction outside that range is risky. And really, it's not very accurate because for all you know, the data might be in a perfectly straight line between 5 and 32. And yet, as soon as we go to $33,000 in ads, all of a sudden it starts to curve the other way. And maybe if we go below $5,000 in ads, it starts to curve the other way up in that direction. So for all you know, you can have an up and down graph, and our data set just happens to be between two curves, so it looks like a straight line. And if you go ahead and make predictions for, if we spend $40,000, $50,000, $100,000, we expect it to get higher, higher, higher. And in reality, it may be turning around, going the other way and doing a dipsy-doodle, and we wouldn't know. We don't have data outside that range, so any predictions we do outside that range is pure guesswork, and I would not do it. So my little comment box actually says not to use a value outside the range of the data when doing your forecasting. Down below further, we've got the hypothesis test for correlation. The hypothesis that's actually being tested is whether or not the slope equals 0, which is another way of saying there is no correlation. Because if there is no correlation, you will not have a line to speak of. I mean, it's going to be a flat line, a slope of 0. We put in our level of significance, and it computes a t-statistic. Don't worry about how you get to that. It does compute a p-value. Notice that pattern. It doesn't matter what tests we did, they all had p-values. The p-value here is 0. We say reject the null hypothesis because it's less than 0.05, and it says conclude that correlation indeed does exist. So we know that there is a relationship. We know that as one goes up, the other goes up. The next slide actually shows what the graph looks like for sales and ads, and you can see what I mean by a linear relationship. I mean, they're just hovering around that line. You don't see much in the way of outliers there. The bottom box, the ANOVA table, we really don't have to bother with that. Correlation is in itself a type of analysis of variance test. So it's common when using statistical software to show an ANOVA table for this. But it's really not necessary for us to go into that. Your focus here is understanding the correlation, the coefficient of determination, what the regression equation is, doing predictions, and doing the actual test for correlation, which in this case is significant. Remember, it's only testing whether or not it's equal to 0. If I took our data set and put in only 2 data points, just 2 data points make a perfectly straight line, guaranteed. If I put in a third data point where it was close to that line, maybe, or even on the line, I would hardly jump to conclusions that, yes, we've proven a perfect relationship, we have a correlation of 1, wow, look at this, isn't it incredible? Well, with any 2 points, you're guaranteed to get an R of 1 or negative 1. If you put a third point in that's close to the line, even though it may come across strong, hardly significant, hardly enough for you to say, I could build my model and make all these forecasts. Yet you have an R that's extremely large, and yet it could turn out to be not significant. Not that it's a bad relationship, but you just don't have enough data to convince us that it is the relationship. On the other hand, if I put in 3 or 4 observations in which they were all over the place and the correlation coefficient was, let's say, 0.1, well, those 3 or 4 points will not show up as being statistically significant. But if I took those same 3 or 4 points and copied them again and again and again in the data set, by the time I got to 100 or 200 data points, my correlation is not going to change. If I've got the exact same 4 points over and over and over again, the correlation is going to stay exactly the same. However, the p-value will continue to get smaller and smaller and smaller until it gets below 0.05 and we say, yep, reject the null hypothesis, even though your correlation is pathetic. That unfortunately happens. The larger the correlation is, the less data you really need to truly make your point. The worse the correlation is, the more data that you would need. But if you're able to throw enough data at anything, you can make anything look like it's statistically significant when it comes to correlation. And that's why I say go the extra step. And if the correlation itself is weak, I really wouldn't push it. And I can, pretty much assure you there's a lot of those that do get published where the correlation is really weak, but because it's statistically significant and they rejected the null, it satisfies the editors a lot of times. But you really have to understand what's going into it so that you can make rational decisions. So we have variables that are correlated. Why are they correlated? There's actually a lot of good reasons. Now remember, I indicated that just because two variables are correlated, that doesn't mean that one caused the other. Although, if one causes the other, they will be correlated. It does work in that direction. If A always causes B, they're going to be correlated. But being correlated doesn't mean A caused B. I came up with 7 reasons why two variables might be correlated. First reason, X really does cause Y, as I put it in our notes here. If one variable literally causes the other to happen, they will by default be correlated. The more you practice your free throws in basketball, the higher your free throw percentage will be. Practice makes perfect. The more you practice, the better your scores. The more hours you studied, the better your grades would be. One literally is causing the other, in some way or another, so it's understandable that they'd be correlated. That's one possibility. I wouldn't jump to the conclusion, but if the causality exists, correlation must exist, not reversed. It's also possible that Y causes X. What I mean by that is there is a causal relationship, but you got it backwards. We see often in sports how teams don't get sellout crowds, and when they lose games, they like to blame it on the fans. Well, if the fans would show up and support us more, we might win. Well, the answer to that is usually if you won, we would actually come out and support you more. It's not our disgrace for not spending a lot of money to go to a game to watch them lose. If they would win, they would drive fans there. But our driving fans there doesn't make them win. So yes, there is a relationship. And yes, there is a causal relationship. But they've got it backwards. Fans don't cause wins, but wins cause fans. Either way, it's still correlated. A third possibility is that X partially causes Y. We know that there's a relationship between exercise and weight loss. Yes, they tell you exercise more, you lose more weight. To a degree, that's true. But diet must be factored. If you do push-ups into a bowl of Twinkies, you're hardly helping your case. Fourth possibility is that there's this third variable, let's call it Z, that's actually causing X and Y to happen. So some other variable is causing these two to happen. But we just don't talk about that. If I were to do a plot of how much money people spend and how much money people save, I would find that there is a correlation, maybe a moderate one, maybe even a strong one, probably moderate. The people who spend the most money tend to save the most money. The people who spend the least amount tend to save the least amount. And why is this true? Simply because they are making more money. People who earn more tend to spend more. People who earn more tend to save more. But if I take the earnings out of the picture and only talk about spending and saving, we go, wow, so your rent is due and you don't have money. Well, go shopping. If you spend it, it will come. Well, obviously that's silly advice. But it's advice nonetheless that you might get if you didn't know what you were doing. You might derive the wrong information from this. It's also possible that we have something called seasonality. It doesn't necessarily have to do with winter, spring, summer, fall, although it could. It could be shopping season, Christmas shopping season. It could be weekday versus weekend. It has to do with the fact that the results go in cycles. So if I were to plot the sales of ice cream and the number of reported cases of the flu, you would find that when ice cream sales are at their highest, reported flu cases are at their lowest, and vice versa. I guess ice cream prevents the flu, huh? No, obviously not. You know, ice cream sales are greatest in the summertime. Flu is greatest in the wintertime. One doesn't cause the other, but they both move according to seasons. And based on that, you might say, I noticed that there's a relationship between the number of Christmas lights that Walmart has in their parking lot or trees in their parking lot versus the number of accidents in the parking lot. Yeah. Do you think that those Christmas lights are blinding them or people get messed up because they see Christmas trees laying around there? No. Then how come the more that's out there, the more accidents there are? Well, during Christmas shopping season, people are driving a little bit crazier. There's more cars there, so you have more inclinations toward having an accident. Coincidentally, we see more trees toward the Christmas shopping season and less afterward. It's seasonal. As you get further into that season, more of that happens. As you get further away, less of it happens, and the accidents go hand in hand. Sometimes we have something called a time series, where it doesn't have to be any kind of cycle. It's just that two things are occurring that are related to time. We might find that there's a relationship between one's shoe size and one's reading ability. I'm focusing on children here. As your child's shoe size grows, his or her reading ability also grows. Does that amaze anybody? I mean, it shouldn't. It's not because people read with their feet or big feet make you smarter or whatever. It's because the older you get, the bigger your feet. The older you get, the better you can read. Let's put those two together and we go, wow, isn't that amazing? But one did not cause the other. Lastly, we would have just sheer coincidence. Sometimes two things just happen to occur. You know, like the daycare issue. You know, changing diapers, burping babies, whatever, and we go, wow, look at this. And we see that we have more in cases of illness when they don't burp the baby and less when they do, but that was hardly the cause. If I took 100 fleas and trained them to jump on my command, and I put them on a table and I yelled jump and they jumped off the table and I gathered them all up and I put them back on the table and I yanked out their left legs with tweezers. You know, as painful as that is, I yell jump and they all jump. I put them back on the table and I yank out their right legs with tweezers and I yell jump and they don't move. Would I then conclude that fleas hear with their right legs? Obviously not. You know, but it is coincidental to what was going on. Now let's move on and take a giant leap. With correlation and regression, we were looking at a relationship between two variables, using one independent variable to predict one dependent variable. More often, though, we're dealing with a lot more than that. I mean, think about what goes into determining if a stock price is likely to go up or down. There's so many different variables people track. What goes into determining if a team is probably going to win or lose? It's not one player's performance, it's a combination of things. We can focus on so many different statistics to try to figure out what's the best model for predicting a team's success. You know, is it ERA, strikeouts, home runs, touchdowns, yards, whatever? You might find there's several variables that combine would make for a good predictor, but no one by itself does the job. And so we will look at multiple regression analysis where we will have several independent variables and one dependent variable. The example I want to use is actually one that's shown as the practice problem on real estate. For that one, I said we were going to use one of the appraisal prices where an agent gave their estimate of how much the home is worth in the appraisal column. And then we looked at variables on the size of the house, whether it has a pool, whether it has a garage, the number of baths, the number of bedrooms, and the age of the house. So you look there, you can see how the data is loaded, and the Y variable, the dependent one, is in that column all by itself, and then the independent variables are in the X columns. They could be in any order, doesn't really matter. Make sure you label it appropriately. Now, for scale variables, you know, seems like it makes sense. We could say, hey, the more the size, the more the price, or the less the size, the more the price, or whatever. But what about when you've got a nominal variable like pool and garage? It's only zeros and ones. How does that work? Well, when you have data like that, it's still okay to use it. If there's two possible values there, we can use it and treat it as what we call a dummy variable. What essentially will happen is if pool turns out to be a factor, it will have some weight put on it such that when the pool value equals 1, the person does have a pool, it will add that number to the total appraisal. When the pool value is equal to 0, it won't add that number. So whatever formula you have where you're multiplying the pool value times a number, you're either multiplying 0 or 1. So you either are adding the number or aren't adding the number. So it works just fine when you have only two possible values, the yes and the no option. It can definitely do that. Generally, you're not going to see a model where the only remaining variables are dummy variables like that, categorical variables. Usually you have to have at least one that's a scale variable, but it is possible to have one or more dummy variables. So I wanted you to see them, and we're going to try them all out. If you load the data in here, just put it in the yellow columns as shown. When you go over to the results page, you see the table at the top, which is called multiple regression results. It shows a column called intercept. The row with the B, that's the actual coefficient, that goes in front of each and every one of the variables in the formula. So for the y-intercept, it's by itself. You would actually say, well, the appraisal price equals minus 31,088, which is the intercept, and then plus 60.5193 times the size, plus 15,109 times pool, plus, and so on and so forth. Each one of those values is a coefficient that goes in front of the variable, but for the y-intercept there is no variable, so it's just by itself. Don't worry so much about the next row, the S of B, that's a standard error. The T is that statistic that we're calculating. We use t-scores, z-scores, depending on the test, chi-square test. This one's a t statistic. It's not really important that you understand the exact t value. We're going to the p-value. And in the bottom row, we see p-values for every one of those variables. The cutoff for significance that we established was 0.05, which means that any one that's less than 0.05 is significant. Whatever's greater than 0.05 right now is not a significant contributor, because basically you want each variable to contribute to the bottom line, to help with the R squared. If I have 4 variables that combined give me an R squared of 82%, but I have 10 variables that combined give me 83%, those extra 6 variables combine for only 1% of more explanation. I'd rather have 4 with 82 than 10 with 83, because it's not really doing much, not giving me bang for my buck, basically. So we're looking to get rid of ones that have high p-values. Well, if we look across here, the p-value for size, 0.0001, that's significant. For pool, 0.0255. For garage, 0. For bath, 0.0005, all good. For the bedrooms, 0.2817, that's greater than 0.05. For age, 0.6470, well, that's greater than 0.05. So something's got to go. Now you notice there is one for intercept, 0.3773. Please disregard those. You're not going to throw out your y-intercept. It's impossible. You don't throw that out. So we don't really make a big deal about the intercept. It's the variables we care about. We only throw out one at a time. You might say, well, why don't we get rid of age and bedroom at the same time? Well, it sounds like a nice, quick, and dirty way to get to the final answer. But there's a problem, and we call it collinearity. It doesn't always exist, but it can. If you imagine that I have 2 variables in there where one of them is the temperature in degrees Celsius and the other one is the temperature in degrees Fahrenheit. When a person's being shown a house, if the house is extremely cold or extremely hot, it might affect the ability to get a sale. But if it's somewhere in the middle, it might do just fine. So let's say the temperature in degrees Celsius and temperature in degrees Fahrenheit are listed there. Well, since those 2 variables pretty much are identical, just that one is a direct translation of the other by formula. If I put both of them in there, let's suppose either variable independently is significant and by itself would contribute 25% to explaining sales. Put them both in there, what happens is it won't show them both contributing 25%. It'll split the difference. It might show each of them contributing 12%. And unfortunately, it might show neither one of them to be significant because the two are fighting with each other to say, no, it's mine, no, I did it, no, I did it. And as a result, they both look bad. But then as soon as you get rid of one, the other one becomes one of your best variables and becomes statistically significant with a high correlation. Because you've got to get rid of one at a time. You don't know what will happen. As soon as you get rid of one, it could affect something else. Because of variables being collinear, they move together. And since they are that way, we've got to treat it this way. So we call this method stepwise regression, where we take out just one. So if I go back to the data page, now I want to remove age because age was the largest number. So I highlight from age all the way down and click delete. Now, it turned out that I've got age already in the far right column. If I didn't, I would need to scoot the other ones over because I've got this set up where the variables need to be, starting from X1 working their way, so you don't want to be skipping columns. But this one works just fine. So now I've got 5 variables left. Now look at the p-values. They're all good except bedrooms. Okay? Bedrooms clearly are not good. So what do I do then? I have to get rid of the entire bedrooms column. I highlight the entire bedrooms column all the way down to the bottom, go back to the results page, look at the p-values, and I notice that all of them are now less than 0.05. Well, I'm done there. Like I said, don't worry about the intercept one, but I've got the rest of them. Looks good. All of them are significant. Now I can move on. You actually can tell what the equation is, too. You could say that the value of the appraisal equals minus 31,074 plus, and then put each one in front of its variable. 64.9423 times the size, 14,096 times the pool, and so on. The value that's the coefficient tells you a lot of information. It tells you one more unit of that item contributes that amount to the bottom line. So that's saying for every additional square foot that your house is over what it is now, the appraised value will go up by about $65. 10 extra square feet, extra $650. So it's telling you one extra of that contributes that amount. An extra bath in the house, it's saying, adds $33,640 to the appraised price. The pool and garage, well, if there is no pool, it just puts a 0 there. If there is a pool, it adds $14,000 to the value. No garage adds 0. With a garage, adds $39,274. So now that we have that in there, we could drop down. Like I said, don't worry about the ANOVA. You notice the R squared, though, 0.5296. It's a moderate relationship. But we got 4 variables there, and it's a moderate relationship. To kind of go back, when I had 6 variables there, the R squared was 0.5373. I now have only 4 variables there, and the R squared is 0.5296, which means not even 1% was lost by getting rid of those 2 variables. They were not doing us much good. Now, this is fictitious data, so don't assume that you won't get value out of knowing the number of bedrooms or the age of the house, but I did make this up, so it's going to have some weird results maybe. So we've got a really good correlation. If we have an R squared of 0.5296, that means our correlation is actually over 0.7. It's actually strong. At the bottom, I can actually do a prediction. I plug in the different values. I plug in the size of the house. I plug in whether or not it has a pool, whether or not it has a garage, how many baths it has, and based on the information that's plugged in, it calculates a predicted value, the appraised value of $253,102, give or take, depending on whether we're doing a prediction interval, confidence interval, but it's going to give us the give or take on that. So we could say for an individual house, $253,000, give or take $63,000. For an average house, it would be give or take $17,000. Nonetheless, really good. And you still are required to abide by the rules of not plugging in numbers outside the range. If I'm not going to go in there and plug in a home with 10,000 square feet when clearly I didn't have any homes even close to that. So I plugged in 2,000 square feet because that was in the range. 3 baths was in the range, and there were definitely some houses with pools and garages. You can go and see that if I take the pool away, you'll notice the price of the appraisal drops by 14,096 because that's how much it contributed to that overall total. So this is how we do stepwise multiple regression. Do it one step at a time until you have your model. You go to the last tab, it's called correlation. We could have looked at this sooner, but there was really no point when we were trying to get rid of variables. You could see how different variables are related to different variables. Nothing seems to be collinear. It doesn't look like any one is highly correlated with any other one. You know, you see that between size and number of baths, 0.0473, nothing to really get bothered by on that one. And yet, when we had all 6 variables there, it turned out that size and number of bedrooms actually had a correlation of greater than 0.3. Number of bedrooms versus number of baths had a correlation of greater than 0.3. So there was some degree of collinearity that it was competing with other variables. Understandable that it would be eliminated from the data set. So what we have left now, we can actually say, fine, we don't need those. We now can see how different variables are related to different variables, in case you were curious what the correlations were. If you just went ahead and just ran a correlation test, a simple regression correlation, as we did earlier in this unit, between baths and home size, you would get that correlation of 0.0473. It would be the same thing. It's just that this one is looking at all the variables at one time. Truly a very powerful tool. There's no limit to what you could throw in there. My attitude is throw in all the variables you can get your hands on, and then you could start deleting them. Sometimes you delete down all the way to one variable. That happens. Sometimes you leave a ton of them. Generally, you won't see models with more than about 5 variables because after a while, no one variable can really contribute that much to the bottom line that it's worth keeping. So generally, you're going to see it capping out at around 5 variables, but a lot of times it'll drop down to 2 or 3 variables, and that's fine. I would much rather predict with fewer variables, and that way I need less information. So if someone says, tell me how much my house is worth, if I only had to ask them their size, the number of baths, and whether they have a pool and garage, that's a whole lot nicer. If I don't have to say, you know, how many closets do you have? How many doorknobs do you have? What's the size of your attic? And so on. If I don't have to ask all those mundane questions because they're not that important, I'd much rather do it this way and extract simple information to make big predictions. And that concludes Unit 7. So here we looked at measuring relationships between 2 variables that were scale-type variables, or relationships between 3 or more variables where we use many variables to predict one, and those variables could be of differing types. Ultimately, we got a model out of it, and we could use that model to make all kinds of forecasts and understand all the different paired relationships. This actually wraps up all of the material in the course. In the next unit, you'll be doing your final data analysis project.